In the previous video, we were using this moving average strategy to explain what exactly is this phenomenon called overfitting, right? So let's look at the three functions that we define. One is the get data function. We used this function to load the data from the disk to the Python script, right? And then the second function, get SMA return, was the function that we used to compute our positions based upon the crossings of the long-term moving average and the short-term moving averages, right? And then using that position computed from this very simple strategy, we can compute the overall return of the entire strategy. Of course, the overall return is going to depend upon S and L, the two parameters, which is actually the window width for the short-term moving average and the long-term moving average, right? And then this function called def get SMA max. This function is basically our training algorithm, right? We were pretty much going through this all possible choices for the S and L, these two parameters, and then try to find the one that actually gives us the maximum return. And we did some experiments, right? We did some experiments by separating our entire data set, which is like 6 years long, right? 6 years of closing price for TQQ, right? And then we separated into the training data, which is about 4 years long, and then the test data, which is a little bit more than 2 years long, right? And then we did the search, we did the training. We called this particular function. We called our training code on the training data. We called our optimization code on the training data, right? On the training data. The training data was so get SMA max. That's the training data, right? We call this function on the training data. That's the training function on the training data. We get the optimal values of S and L, the window width for the short-term averaging and moving average and the long-term moving average, right? And what we have found is that if we apply the same set of optimal parameters that we obtained from the training data to the testing data, right, which was never exposed to the training algorithm, right? We never actually called get SMA max on the testing data, right? If we apply the same set of optimal parameters on the testing data that was never exposed to the training process, the return was actually not so good, right? So on the training data, the return was like close to like it's actually over 6%, 600%, right? It was about 600% on the training data. But if you apply the same set of same set of optimal parameters to the testing data, what you get is 1.38% on the testing data for 2 years, right? That was a phenomenon that's called overfitting, right? Because the optimal parameter that you obtained was from the training data, right? And the testing data could have some characteristics that's different from the training data, which makes the optimal value that you found for the on the training data not exactly the optimal value for the testing data, right? And we did some optimization on the testing data also, right? This piece of code was pretty much just the testing. Applying the same training algorithm, which is this brute force search on the testing data, right? And what we found is that if you actually try to train using the testing data, you can actually get to like 700% or something on the testing data for the 2 years of data, right? But in reality, this is actually not realistic because the testing data could be the future data, right? In practice, you never know what's gonna be the future data, right? So you cannot actually do your training on the testing data. So testing data has to be set aside and never give it to the training algorithm, right? And that's sort of the problem with overfitting, not just for this simple algorithm based upon the crossings of the two moving averages, but also for any kind of machine learning algorithm. You have this kind of problem because you never know what's going to be the future data, right? Today we're going to sort of look at neural networks, right? So the purpose of this sequence of videos is not to actually look at this kind of classic method, very classic method based upon moving average, but look at new techniques based upon neural networks, right? And in the video that I made a few days ago or a few weeks ago, I was saying that reinforcement learning is the right way to go because it takes into account this delayed reward, right? And delayed reward is probably the essence of investing, right? You have to account for this kind of delayed reward. But the problem with reinforcement learning is that it is actually a unsupervised learning technique, right? Unsupervised learning technique means what? Means there's no correct answer for every action that you take. The correct answer is not given to you. It's not given to you like those supervised learning. You have a label, right? For supervised learning, for every feature you have a label. But for unsupervised learning, it's not the case. You don't really have a label that's given to you, right? So let's take some baby steps. Right? So before we move on to using reinforcement learning to account for this kind of delayed reward, let's use supervised learning. Right? What does supervised learning allow you to account for, right? Remember that in the Bellman equation, the first term on the right-hand side is actually the direct reward, right? So the total value of a certain action in a certain state is actually the direct reward plus those delayed reward, right? But discounted according to a certain factor, right? So can we use supervised learning to account for direct reward? Can we do that? Right? And if we can do that, then maybe we can sort of take some baby steps towards our eventual goal of using reinforcement learning to account for delayed rewards, right? Yes, we can do that. What exactly is the direct reward in this context, right? What exactly is the direct reward? Don't forget, we have price fluctuations from day to day, right? The closing price changes from day to day. So if we take a certain position, say a long position today, and the closing price for our instrument increases tomorrow, right? Which means we don't have to wait for like 1 week or 1 month or several years to get our delayed reward, right? We can just get our direct reward the next day, right? And if we are taking a short position today, but the next day the price of the instrument drops, then we have a direct negative reward, which is actually a penalty, right? And this next day price change, whether it's increasing or decreasing, it's a direct reward. It's not a indirect reward that you have to wait for like multiple days in order to actually realize, right? That's a direct reward. And if we just want to account for this kind of direct reward, it's actually possible for us to do some supervised training because at least for the training data, we know what's going to be the direction of the price movement the next day, right? The next day. So let's try to use this kind of a supervised learning to study how do we account for direct rewards, and it's gonna also allow us to take a look at how to use Keras, this high-level machine learning API or deep learning API that allows us to construct neural networks very, very easily, right? So let's create a new file. Let's just call it direct. And then for neural networks, there can be lots of different structures. And the shape of the neural network could be dependent upon the purpose of the algorithm, right? So some of you probably have heard about the convolutional neural network, so CNN, right? Recurrent neural network, RNN, right? Lots of different shapes that's built for different purposes, right? Before we actually get into that, that's a huge topic by itself. But before we get into that, let's just use those fully connected dense neural networks. So every connection is like between every neurons we have between neurons of consecutive layers we have the full connections, right? So let's call it, it's a dense network, right? Let's call it direct dense.py. Let me see. Oh, maybe let me just get rid of this old code, and I'm gonna restart from the beginning, right? Let me just delete it, and then we can start over again. But before we start our coding, let's look at this disclaimer, right? All examples and the code presented in any of my YouTube videos are technical and illustrative in nature and do not represent any financial recommendation or investment advice, right? So now let's create that direct dance.py, right? Okay. So before we actually start writing new codes, let's just copy over this piece of code that we're going to use to read the data. Right? So we are going to use the same function to read the data. Right? But before we actually put together our training data, let's try to decide what kind of a training information, or what kind of a feature set that we want to feed into. We want to feed into the neural network, right? The closing price is certainly just one feature, right? That's the price itself. But there are other things that we might want to sort of add to the feature list, right? So let's define a function called feature. Create features. And this create features function is going to take a data frame, right? And then I'm going to give it two more parameters. One is called legs, and the other one is called window, right? What's the purpose of these two parameters, right? We looked at the windows parameter when we were doing this kind of a moving average algorithm, right? The windows allows you to actually take a moving window with a fixed width and then compute the averages within the sliding window, right? And that algorithm allows us to actually take a look at the average closing price through a moving window, right? And in our feature set, we are also going to use the simple moving average as one of our features, right? We're going to use the simple moving average with a window width. That's the input, right? And the default window width is going to be just 5 days, for example, right? For example, it doesn't have to be 5 days, right? And then what's going to be the legs, right? What's going to be the legs input parameter? The reason that we are adding this input parameter is because for the time series data, like stock prices, it has a certain ordering, right? It has a certain ordering. If the ordering is different, it's actually a different time series, right? It's a different time series. So the ordering with time is actually kind of important because it contains information, right? You cannot not just shuffle around all the different numbers in different orders and say that's the stock price. It's not, right? For a certain stock, the price movement has ordering, right, from day to day. And how do you actually take into account this kind of ordering in the data, right? This temporal dependence or temporal ordering of the data, right? The ideal tool that we can use to account for this kind of a ordering information is to use something that's called a recurrent neural network, right? But we are going to postpone that to a later time because the topic itself is pretty big and it requires lots of research, and we can sort of discuss that in a lot more detail in a later video. But for now, how do we account for this kind of ordering, right? So in our feature set, we are gonna account for not just today's closing price, but the closing price 5 days before, right? So pretty much just the default value is 5 days, but you can change that. Right? So whatever feature that we are going to use, we're not going to just use it 1 day. We are going to use like 5 days before, right? And by doing that, we can sort of imitate this kind of a short-term memory of the neural network that's provided by some more specialized structure like a recurrent neural network, right? So here we're just adding those historical or past 5 days of feature data as different sets of features, right? So that's going to allow us to actually account for to give our dense neural network some kind of memory in time, right? So that's the purpose of this second parameter. And then let's just create our feature list, right? So I'm not going to change the input data itself, so I'm just going to make a copy of it, right? And then my data frame is stored inside of this df, right? And then let me just drop an a. Right, and now let's try to actually construct our feature list, a list of features. Right? So the first thing I'm gonna construct is this return feature. That's pretty much just the day-to-day fluctuation in the closing price, right? And I'm gonna take the log of it. Right. In the previous example, we were using C return or CR as the closing price day-to-day fluctuation, right? And I'm gonna just do df divided by it's probably dfc, the closing price, right? Divided by df closing price c dot shift by 1, right? That's gonna be our day-to-day return, right? That's the day-to-day return. And then the second parameter I'm gonna define a second feature set that I'm gonna define is called the momentum, MOM. I'm just gonna shorthand denote it as momentum, right? And then it's gonna be the df return that I have defined above. And then I'm gonna taking a moving window with width window, right? And then I'm gonna compute the mean. So this momentum is actually computed on the return data, right? It's a moving average of the return data, and I'm calling it the momentum, right? And then I'm gonna compute something else that's called volatility. Volatility, I'm just gonna shorthand denote it as VOL. It's also gonna be computed on the return data, right? But it's a moving average with a width window, and then it's not the mean, it's not the average, but standard deviation, STD. So all those functions were provided by pandas, so I can just call them without any kind of any problem. And then I'm going to define my SMA. That's the moving average, right? That's the moving average, and the moving average is going to be the closing price the moving average of the closing price. So you have to distinguish these two different features, right? Momentum and the SMA. Momentum is the rolling average or moving average of the return data, of the return feature. And then SMA is actually the moving average of the closing price of the instrument. And then I'm going to define something that's called a bias. BIS. That's the bias. That's the closing price subtract the moving average of the closing price, right? So let's just let's call it bias, right? For the name, that's a shorthand notation about bias. Okay. And then I'm gonna define another feature that's called a mean, and the mean is gonna equal to what? Mean is gonna be defined as the mean of the bias data within the window that we have defined. And then df max is going to equal to df bis dot rolling window dot max, right? And at this point, I need to drop an a. Right. So what kind of feature to use is by itself a big topic, because in practice, lots of traders are using many different kinds of technical indicators, right? Some of the indicators can be easily computed by just using those internal functions of pandas. So some of those momentum, volatility, bias, min max, these kind of indicators can be easily computed by using pandas, right? there are other more sophisticated indicators, right? Some people use so-called MACD or something, right? MACD. That's called a moving average, convergence, divergence. In Asia, people use something that's called KDJ. KDJ is some kind of a volatility index, right? It shows you how it's kind of a it has similarities with this kind of RSI indicators, that kind of thing. But here we are just using some of those very easily computed technical indicators, right? And what might be the best set of indicators, or what might be the best set of indicators to be used as the features for training a neural network? This is a research topic, and nobody knows that yet. But what I can say is that for many of those indicators, they have information that's kind of duplicating each other, so they are not exactly all unique. Some of the indicators can have some duplicating information with other indicators, right? What you want to do what you want to use as a feature list for training a neural network, you want the information to be more or less independent of each other. You don't want lots of duplicate information, right? But for now, let's just use this set of information, this set of feature list, right? We can try different indicators later on, right? Once we have a function that's set up already, and see if we can build in some more sophisticated indicators and improve the performance of our neural network, right? Okay, so that's gonna be the set of 1, 2, 3, 4, 5, 6, 7, seven features that we're gonna use, right? And then don't forget, we also need some kind of label, right? For direct reward, we're gonna create the label by ourselves. So how do we actually create the label, right? How do we actually create the label? It's actually quite easy. So df, we're gonna define another feature called direct reward, DRD, right? Direct reward. That's gonna be equal to amp.where. So df ret, if the return is larger than 0, and then the label is going to be what? The label is going to be 1. And then otherwise, the label is going to be 0, right? That's going to be our direct reward label. So if our position is long, and the next day the return was positive, then it's correct. The label is going to be 1, right? It's a correct choice. But if our position is long and the next day the return was negative, then it's a wrong choice. Then our label is going to be 0, right? That's going to be our label. That's going to be our label, right? So now let's deal with this lags information, right? What we are saying is that all those features were instantaneous, so it changes from day to day, right? But how do we actually build in some kind of a short-term memory for our neural network, right? In the future, when we talk about recurrent neural networks, we can build in long-term memory, so the data can remember, the network can remember data from like a very distant past, right? But for now, let's just use these lags to build in some kind of short-term memory, right? But without using recurrent neural networks, right? Let's try to do that. The features that we want to duplicate for the lags, it's gonna be, let's construct a list, right? RET, DRD. That's our labels, right? DRD, direct reward, and then the momentum, the volatility. The ordering doesn't really matter too much because it's just gonna be, you're gonna index into the data frame by using the name of those features, right? VOL and then SMA. Do we really want to use SMA? Let me drop SMA for now, right? Because SMA has an absolute value inside of it, right? And every other indicators are kind of more or less relative, right? And later on, once we start to work on the code, you will understand why we want to drop this SMA, right? BIS, bias, min, max, right? So that's going to be our feature list. And then we're going to sort of create a set of columns based upon this this feature list, right? So for f in features, and then for lag in range 1 to what? 1 to lags plus 1, right? And then call, we have to actually construct a name for the different columns of our data frame table, and we are going to use this Python formatted strings. It's going to be the feature, right? It's going to be the feature. It's going to be the feature, and then with an underscore, lag underscore, and then lag, right? So this f is going to be replaced in here, right? And this lag is going to be replaced with this lag, with the actual value of this particular lag, this iterator, right? And this whole string, that's going to be a string, right? This whole string is going to be the different columns inside of our codes list, right? So df code is going to equal to df f dot shift by lag, right? And then codes dot append code, and then let's just df drop in a, right? And then we can just return df codes, both the data frame and also the name of all the different columns that we are going to use for our training purposes, right? And that's going to be our function for creating all the different features, right? But maybe now it's a good time for us to actually try out this particular function, see if we have made any mistakes, right? So data is going to equal to get data, say still give it tqq, right? And then let's just do a data codes equal to create features data. Let's just use all the default values, right? So the lags are going to be 5, and then window is going to be 5, and then let's just data.info, right? Let's look at the result of this calculation, right? And let's just run below and see what's going to happen. Okay, looks like we the code is good, right? So for every feature we want to use for in our training purpose, for our training purpose, we have created one lag. So ret underscore lag underscore 1 is the return data lagged one day, lagged by 1 day. That's from yesterday, right? This is lagged by 2 days. That's the day before yesterday, right? So by doing this kind of additional feature that's coming from 5 days prior, we can build into the neural network some kind of 5-day memory, right? That's our ad hoc way of let the network remember like 5 days of information, right? Without using the recurrent neural network. So that's it for this video, and in the next video we are gonna build our neural network and then do some training on it and see how good it is compared with our kind of a 2 moving average strategy, right? Thank you.